Okay, all you freshers out there, listen up. You've spent years with your head in the books, right? But let me tell you, the real world, the plant floor, that's a completely different beast. So today, we're going to bridge that gap. We are talking about thermocouples. And by the end of this, you won't just know the theory, you'll start thinking like a seasoned plant professional. Let's get right into it. First things first. Why should you care so much about this one little sensor? Well, because the answer to this question is temperature. I don't care if you're in a massive refinery, a food processing unit, or a power plant. Temperature is almost always the most critical variable you have to control. You get it wrong, and you're not just making a bad product, you could be heading for a catastrophic failure. Seriously. When it comes to measuring temperature on the plant floor, the undisputed king is the thermocouple. It looks so simple, right? Just a piece of metal. But it is the absolute workhorse of our entire industry. And I'll tell you this, understanding it deeply, practically, that is what will separate you from every other fresher walking into that job interview. Now, don't you worry, I'm not going to start throwing complex equations at you. We're going to cover the core science, sure, but only the parts that truly matter when you're standing in front of a control panel trying to figure out why a reading has gone crazy. This is the practical physics you actually need to know. So it all comes down to something called the Seebeck Effect. It's actually pretty simple. You take two different types of metal wire, you weld them together at one end, and you apply heat. That's it. The temperature difference between this hot measuring junction and the cooler end generates a tiny, predictable voltage. And the crucial part, as you can see, is that it needs no external power. The thermocouple literally creates its own signal, which makes it an incredibly simple and tough active sensor. But just how tiny is this signal? Well, a standard Type K thermocouple, the one you'll see most often, produces only about 41 microvolts for every degree Celsius. That's millionths of a volt. To put that in perspective, it's like trying to hear someone whisper in the middle of a noisy factory full of huge motors and variable frequency drives, VFDs. This tiny signal is super susceptible to all that electrical noise, and managing that is a huge part of the job. All right, I need you to pay very close attention now. If you only remember one thing from this entire explainer, make it this: cold junction compensation, or CJC. I absolutely guarantee you this topic will come up in your technical interviews. You master this concept, and you will immediately stand out from the crowd. So here's the crucial point, and it's a trap so many freshers fall into. A thermocouple is a differential device. It doesn't actually measure that the process is at, say, 500 degrees. No. All it measures is the temperature difference between the hot tip, way out in the pipe, and the so-called cold end, where the wires connect to your control system. And this question right here perfectly illustrates the problem. Just imagine, your control panel is in a room that's a cool 20 degrees in the morning, but by the afternoon, with all the electronics running, the panel heats up to 35 degrees. Your cold reference point has just changed by 15 degrees. So even if the process temperature never moved an inch, the voltage from the thermocouple will change, and your reading will be completely wrong. So how on earth do we solve this? Well, modern technology does all the hard work for us. Let's just walk through these steps. See, inside your control panel, the thermocouple connects to an input card on a PLC. That's the brain of the system. First, there's a tiny thermistor on that card that's constantly measuring the panel's temperature. That's our cold junction. Second, the card reads that raw millivolt signal coming in. And third, this is the magic part. The PLC's brain automatically adds that cold junction temperature to the temperature it calculated from the millivolts. And the result? A true, compensated, and perfectly accurate temperature reading. That, my friends, is cold junction compensation. Okay, so now you get how the signal works. Let's talk about the actual physical hardware. Because as an engineer, you're the one who's going to be selecting these sensors. And your first big choice is about how the tip itself is actually built. You've basically got two main choices. In a grounded junction, the sensor tip is welded directly to the outer metal sheath. This gives you a super fast response to temperature changes, which is great. But it can also act like an antenna and pick up electrical noise. Now, in an ungrounded junction, the tip is insulated from that sheath. This makes it pretty much immune to noise, but it's going to respond just a little bit slower. It's a classic engineering trade-off. Do you need speed or do you need a cleaner signal? Next up, you have to choose the type, which is just denoted by a letter. Look, Type K is your all-around industry standard. It's the workhorse you'll see everywhere. Type T is fantastic for low temperatures. Think food processing, cryogenics, that sort of thing. But look at Type J. It's really common in the plastics industry, but here is your pro tip. Never, ever, ever use a Type J where moisture could be present. The iron wire inside it will literally rust and your sensor will fail. It's a guarantee.
Knowing all this theory is one thing, but installing it correctly on the plant floor is what prevents disasters. So listen up, there are 2 rules that are absolutely 100% non-negotiable.
Rule number 1, always use a thermowell. What is it? It's just a solid metal sleeve that gets permanently installed in the pipe. The thermocouple just slides right inside it. Now, why is this so critical? Imagine you have to replace a failed sensor that's in a high-pressure steam line. Without a thermowell, you'd have to shut down the entire plant. With one, you just pull the old sensor out and slide a new one in. No shutdown, no lost production. It's a lifesaver. Rule number 2, and this is a massive mistake I see freshers make all the time. You absolutely cannot use regular copper electrical wire to run the signal from the thermocouple back to the control panel. Remember the Seebeck Effect? If you connect copper to those special thermocouple alloys, you've just created 2 new unwanted thermocouples right there at the connection point. You'll completely corrupt your signal. You must use the proper extension wire, which is made of the exact same alloys. No shortcuts. All right, you've specified it, you've installed it, but what happens when an alarm on the screen starts flashing at 3 a.m.? Now you need to troubleshoot. It's time to stop thinking like a student and start thinking like a real plant pro. Let's look at the top 3 culprits. First, burnout. This is just a simple open circuit. The little welded tip breaks. Your PLC will see this and typically drive the reading all the way to its maximum value, giving you a very clear alarm. Second, reversed polarity. This is a classic rookie mistake. In North America, the red wire is negative. Yeah, I know. If you wire it backwards, the temperature on your screen will actually go down as the process heats up. Finally, an internal short. If the insulation inside the probe fails, the wires can touch each other, creating a new junction. Now you're not measuring the temperature at the tip anymore. You're measuring it somewhere in the middle of the probe. So let's bring it all together, okay? Cold junction compensation, the critical importance of thermowells, choosing the right junction and type for the job, and knowing how to troubleshoot the most common failures. You master these practical concepts, and I promise you, when you walk into that interview, you're not just another graduate with a degree. You are an industry-ready engineer that they need to hire. But the learning never ever stops. This is just the beginning of building that real-world practical knowledge that is going to define your entire career. If you found this useful, make sure you join us here at the Industrial Automation Hub for more explainers just like this, designed to make you a top-tier automation professional. Stay sharp, everyone.